All the
Yes, ma'am.
call is now being recorded. Today's topic is heteroscedasticity. In a linear regression model, we assume that error term has a normal distribution with mean 0 and variance sigma square. So simply, if I introduce the idea, variance of ui is equal to sigma square. If I consider a k variable model, as you found, whenever we will consider variance of ui, actually you will get the variance covariance matrix of ui, and all the variance terms will appear in the diagonal. Along the diagonal, you will get the variance terms, and these variance terms are all constant. Now, when the error term does not have the constant variance, in that case, we have to present it by sigma I square. It is varying as we are moving from one group to other for a cross-section analysis for different income levels, say, or for different regions, say. Okay. I can again consider the simple example of income and consumption. Consumption is a function of income. You know that across income classes, MPC does not remain same. There will be, changes which are very much observable. Okay. If you consider different part of the country and you construct the similar kind of analysis, you will find that depending on the culture, etc., the income consumption relationship is varying a lot. Okay. So if this is the context, we present variance of ui as sigma I square. So instead of consumption and income, you can consider savings and income, the same sort of analysis or same sort of aspects will appear here. So these are the presentations for the saving equation. Okay. It's a three-dimensional picture. In the first case, what we are finding that this is a positively sloped line, We know that as income increases, mildly there will be an increase in savings. It is similar to that of the consumption function. If you, instead of savings, if you consider the consumption function and think about your macroeconomic context, you will find that it is mildly rising function. Okay. And actually there are scatters along this particular line. This line is a fit along the scatters. Now homoscedasticity indicates the distribution of the scatters around these equation beta 1 plus beta 2 xi remains similar as we move from income level 1 to income level 2 to income level 3, etc. Okay. Along this axis, we are measuring the probability density. You are finding that both the height as well as the breadth of the normal curves, that is the distribution of the scatter around the line, these are very, very similar as we are changing the income level from this point to this point to this point, etc. However, if we consider the second diagram, we are finding that both the spread as well as the peak, everything is changing, So here the peakedness is very high, mean concentration is very high, Here the spread is mesokurtic and here it is platykurtic. So the distribution of the scatter around the line is changing as we are moving from low income group to high income group. Okay, so this is the idea. So pattern of saving is very, very similar in a low income group. It is changing for middle income and it is changing a lot. The spread is, very high. Platykurtic distribution in context of high income group. So the first diagram is indicating homoscedastic distribution of the scatters around the line, and therefore the error distribution is homoscedastic. In the second case, the error distribution is heteroscedastic. We can recall our regression model, which we considered at the undergraduate level, the simple two-variable model. yi is equal to say alpha 1 plus alpha 2 xi plus ui. If the error term ui is homoscedastic with variance sigma square, we know that we will get the blue estimators and the values of the blue estimator. We are more interested about the gradient term. So the blue estimator is given by alpha 2 hat, which is summation xi yi divided by summation xi square. And its variance will be given by sigma square divided by summation xi square. Now, instead of homoscedasticity, if we invite heteroscedasticity, the structure of alpha 2 hat will not change. The estimated value will not change. Still, it will be based on the initial regression model. So yi is equal to alpha 1 plus alpha 2 xi plus ui. There will be no change in the estimation process. And you can present the estimator as summation xi yi divided by summation xi square. However, if I present the variance of alpha 2 hat, it is no longer sigma square by summation xi square. We will find that it is becoming summation xi square sigma I square divided by summation xi square whole square. So as we elaborate in the next step, I'll elaborate the things. You will be able to find out these values. Actually, in case of homoscedasticity also, we get this kind of estimator. Since sigma square is a constant, we can keep it outside the range of summation. And as I do so, I can cancel one summation xi square, and finally the measure reduces to this one. However, in case of heteroscedasticity, since sigma I square is varying with I, we cannot keep it outside the range of the sum and we cannot make adjustment. So it will remain like this, and clearly it is not equal to sigma square by summation xi square. So what we are finding that we can still minimize residual sum of square and can find out the values of the estimator. However, the main problem will appear if we move to calculation of variance of alpha 2 hat. And if variance of alpha 2 hat does not provide us the minimum variance, then the best property of the estimator will be naturally gone. It will vanish. Okay. And for that matter, this estimator will give all erroneous conclusion. If you do something based on these variances, your inference will be wrong. So all these consequences will start. So if I jot down the consequences of heteroscedasticity for applying ordinary least square technique, the first consequence we are marking as OLS is still unbiased and consistent under heteroscedasticity. We will show it. OLS is still unbiased and consistent under heteroscedasticity. Interpretation of R square is not changed. It will also remain unchanged. That is the measure of goodness of fit. That will also remain unchanged. The interpretation will remain unchanged. However, heteroscedasticity invalidates variance formula for OLS estimators. So under heteroscedasticity, OLS is no longer based linear unbiased estimator. There may be more efficient linear estimators. And finally, the usual t-tests are not valid under heteroscedasticity. Hope you are understanding the matter, because your estimated value is not blue. Your variance calculation is not the minimum variance, and therefore the t, which is beta hat divided by standard error of beta hat, that will not be valid under heteroscedasticity because it will give you all erroneous conclusion. So one by one, we will look at these consequences. That is, we are still getting the unbiased estimator. However, the minimum variance property is not retained. T statistic is not, the desirable one. So one by one, we will do this. So please bring your pen and paper, because today we will do something, for which you need the pen and paper. So please write down. Let's consider a simple regression model in the deviation form. Let's consider a simple regression model in the deviation form. So small yi is equal to beta small xi plus ui. Model in the deviation form. Small yi, that is capital yi minus y bar. And small xi. This is the position. And all of you know, when we consider the deviation form, the intercept term will vanish. Model assumptions are as follows. Expectation of ui is equal to 0, first assumption. Second assumption is regarding the variance as well as the covariances. Variance of ui is equal to expectation of ui square, which is equal to sigma I square. Expectation of ui uj, that is the covariance part, is still equal to 0 for all I not equal to j. Here you please write down for all I. And the third assumption is X is non-stochastic. Third assumption is X is non-stochastic. You know the formula for beta hat OLS? Summation xi yi divided by summation xi square. Now we will check whether this beta hat OLS is unbiased, whether it is giving the minimum variance or not. So in place of yi, please write down beta xi plus ui. Replace yi by beta xi plus ui. So you are getting beta summation xi square plus summation xi ui divided by summation xi square. So this is equal to this one. So expectation of beta hat is equal to expectation of beta plus summation xi ui divided by summation xi square. Now expectation of beta is beta, since beta is a constant. And for the second term, you will operate expectation on ui. So it will be summation xi into expectation of ui divided by summation xi square. Since expectation of ui is equal to 0, the second term will vanish when you will consider the expectation. So safely we can write expectation of beta hat is equal to beta. Next, we will consider variance of beta hat. Okay, so please note down expectation of beta hat is equal to beta, and these beta hat is nothing but OLS. And this implies, please add, in presence of heteroscedasticity, The OLS estimator is still unbiased. In presence of heteroscedasticity, the OLS estimator is still unbiased. Next, we move to calculation of variance of beta hat OLS. It will be expectation of beta hat minus expectation of beta hat whole square. Now already we got expectation of beta hat is equal to beta, so we can safely write expectation of beta hat minus beta whole square. Now what is the value of beta hat minus beta? You know, we earlier got that beta hat OLS is equal to beta plus summation xi ui divided by summation xi square. So beta hat minus beta, that will be simply summation xi yi, summation xi ui divided by summation xi square. So expectation of beta hat minus beta whole square can be presented as expectation summation xi ui divided by summation xi square whole square of this. Any question up to this? Any question, any query? I'm writing or I'm keeping this part, that is whole square of 1 by summation xi square outside the range of expectation as we are considering non-stochastic xi, and then I need the spread of these summation xi ui along with expectation. Okay, so Choyon, please tell me what will be the spread, what will be the formula. I have to write whole square of summation xi ui. Okay, I have to consider the spread of square of summation xi ui, and along with that I'll also operate expectation on error part. So tell me what will be the spread. It is summation xi ui whole square of that. So Choyon,
Yes, ma'am.
yeah. So please tell me what will be the spread of summation xi ui whole square of that. Okay, just I'm asking the class 11 level thing. Please write down the matter and Hello? Yes, Chayan? Hello, please unmute yourself, Chayan.
Yes, ma'am.
Hello. A plus B whole square এর ফর্মুলা কি ভুলে গেছো?
Ma'am, না a
তাহলে
square
বলো।
plus 2ab plus b square.
হ্যাঁ, তাহলে বলো কি হবে? Summation xi ui whole square. What will be the thing? Same thing is there. x1 u1 plus x2 u2 plus up to xn un তার whole square. So what will be the thing?
ম্যাম একটা টার্ম হবে এক্স আই জে আই নট ইকুয়াল টু জে।
I want to know what will be the formula for summation xi ui whole square of that. So what will be the thing? What will be the formula? Shreya?
Ma'am, summation of xi square ui square plus summation like double summation ui just a second. Double summation xi xj ui uj.
Very good. This will be the thing. This is a plus b whole square. So if I write the thing, so it will be summation xi square. Since I am at the same time operating the expectation, she said summation xi squared ui squared. I am also doing the same. Just I am operating expectation on this plus xi, xj. This is the matter. Again, xi, xj, ui, uj, I am operating expectation on ui, uj part. Okay. Is it okay to everyone? Orkodip,
Yes, ma'am.
you are understanding the matter?
No, ma'am.
So now I'll follow the assumptions. Expectation of ui square is equal to sigma I square. And expectation of ui, uj, that is equal to 0. So the second term will vanish as expectation of ui, uj is equal to 0. So this can be presented as okay. So this was the formula which I presented in the PowerPoint. Variance of beta hat OLS is this one. Okay. So please write down. Therefore, minimum variance property of OLS estimators no longer hold. Minimum variance property, therefore, minimum variance property of the OLS estimator no longer holds. Thus, beta hat OLS is not the blue And
Ma'am, does beta hat OLS?
is not the blue best linear unbiased estimator, not the blue best linear unbiased estimator, and Gauss-Markov theorem does not hold. Okay. So this is the consequence of heteroscedasticity. OLS estimators are still unbiased. However, these are not blue. Already I mentioned the interpretation of R square will remain same. However, as the estimators are not blue, T statistics will be either the overestimates or the underestimates, and naturally these are all improper. So this is all about the consequence of heteroscedasticity. Okay, consequences of heteroscedasticity. The OLS method treats every observation equally and does not take heteroscedasticity into account. So we can make this kind of conclusion. Therefore, we have to change the method of estimation here. We have to move for generalized least square estimation technique. Okay. So OLS we are finding will be not suitable because it will be not able to give us the best estimator. And therefore all T statistics, everything will be erroneous, because the main problem with OLS is it treats every observation equally and does not take into account the heterogeneity in the variances. Okay, and therefore we will move towards generalized least square method of estimation. So again, we are considering the model yi is equal to beta 1 plus beta 2 x 1I plus ui. Variance of ui is equal to sigma I square. Rest of the assumptions of ordinary model will hold good. Only this assumption is varying. So what we are doing, we are transforming the model, dividing it by 1 by root over wi, where this wi is equal to 1 upon sigma I square. In the last class, while I introduced GLS, I talked about omega inverse, because I presented the entire thing in terms of matrix algebra. So actually we considered the variance covariance matrix and considered inverse of that. Today I have started with the simple regression model. Okay. And in case of simple regression model, we presented the assumption of the error term as, the second assumption of the error term as, there is disturbance in the variance part. However, the covariance part is not disturbed. So instead of omega inverse, I am considering sigma I square and taking 1 by sigma I square. I hope you are understanding. Conceptually, I am doing the same thing. I'm considering 1 upon sigma I square. And in case of matrix algebra, when I presented GLS, I considered omega inverse. Okay. Now, when I'm considering this kind of Wi, taking root over of these, and Wi is equal to 1 upon sigma I square, the variance should be known up to a multiplicative constant. Again, later I'll bring this issue. So you can either write this variance as sigma I square is equal to, say, sigma square into xi. Then also it is varying, because xi is varying when I am changing the observation. Okay, so we call it sigma I square is known up to a multiplicative constant. Now to begin with, to introduce the GLS technique, since I am writing sigma I square, I am considering sigma I square is known. Okay, or sigma I is known. So I can start with this, sigma I is known. It is varying, however, I have knowledge about sigma 1, sigma 2 up to sigma n. Or I can present the matter in this format, sigma I square is equal to sigma square xi. I have data on x, it is varying across observations, and I can present the thing in this way too. Okay. Then I am dividing the regression model, or rather, I'm multiplying the regression model with the weight. The weight is 1 upon root over wi, where wi is equal to 1 by sigma I square. Okay. So in place of wi or root over wi, I'm putting 1 upon sigma I square. So basically, the weight is okay, this one. This is the weight. So once I get this weight, I'm transforming the model. Using the transformer okay. Last year I talked about P. I talked about P in context of GLS. P is the transformer. It is transforming omega in such a way so that when we are transforming the model, we can get back the best linear unbiased estimator. So here I am trying to find out a weight which will be treated as transformer, and we need to check while we are transforming whether we get back the best linear unbiased estimator or not. So I'm deflating, the entire model by sigma I, okay, or multiplying the entire model by 1 by root over wi. Sorry, dividing the entire model by 1 by root over wi, and getting the transformed equation yi by sigma I is equal to beta 1 plus 1 upon sigma I plus beta 2, xi by sigma I plus ui by sigma I. So let me know if anyone has any problem, any doubt regarding the transformed equation. This 1 by root over wi, this is transformer. Or alternatively, you can say sigma I is the transformer. Anyone, any question? So the transformed model is becoming yi star is equal to beta 1. I am calling 1 upon sigma I x naught I star beta 2 x 1 I star plus ui star, where ui star is equal to ui by sigma I is the new error term in the new model. Now variance of ui by sigma I is equal to 1. So please do the steps and tell me the steps how I can write variance of ui by sigma I is equal to 1. If I can show this, in that case, this new error term will be homoscedastic, because it will become a constant equal to 1. Consider variance of ui by sigma I. Is it equal to 1 or not?
Yes, ma'am.
Okay, please explain why you are telling yes.
Well, variance of ui by sigma I, we can write 1 by sigma I square into variance of ui, and variance of ui is sigma I square. So sigma I square by sigma I square is 1.
Slowly, please, so that I can write whatever you are telling.
Yes, ma'am.
Follow.
And we can write this as 1 by sigma I square
1 by sigma I square, okay?
into variance of ui equal to sigma I square.
I hope you are telling that.
Yes, ma'am. 1 by sigma I square.
Is equal to sigma I square, and therefore the matter is like this.
Yes,
Everybody
ma'am.
agree with this? Is it okay to everyone?
Yes, ma'am.
Okay. So very good. So while variance of ui is not a constant, variance of ui by sigma I is a constant, and therefore now the variance is homoscedastic. So we call beta 1 star, beta 1 hat star, beta 2 hat star the GLS estimators. Okay. And the estimated regression model becomes this: yi star hat is equal to beta 1 hat star x naught I star plus beta 2 hat star x 1 I star, etc. Okay. Now, in the next step, to find out the GLS estimator, we minimize the residual sum of square. Now, the residual sum of square will be calculated on the basis of ui star, not ui star. So, the formula for residual sum of squares, that will be given by ui hat star square of that. Is this part, the left hand side, is okay to all of you? Are you understanding? This is the model. This is the regression model. yi star is equal to beta 1 x naught I star plus beta 2 x 1 I star plus ui star. This is your transformed model. And to find out basically this beta 1 hat star, beta 2 hat star, you need to minimize residual sum of squares, RSS, residual sum of squares. Now, residual in a standard model, what we do? We consider summation EI square. Now, what is EI? You know, EI is some sort of estimator of UI. So, in a standard model, what is EI? EI is equivalent to UI hat. So in this case, if I mark the residual as EI star, it is basically this one. So I'm considering that as residual. I'm considering the notation UI hat star or UI star hat of UI star. And I'm taking sum of squares of that, which is equivalent to say, I'm considering the last estimated model was this one. It is given by this one, beta 1 star, etc. You know, so for the estimated values only we can do it. So I am getting summation yi star hat, etc. And we will simply minimize this subject to beta 1 star hat and beta 2 star hat and find out this estimated value. Okay. So what will be your homework is to just take derivative of this one with respect to beta 1 hat star, beta 2 hat star, take the derivatives, set the values equal to 0. So you will get the normal equations. Solving the normal equation, check whether you are getting this kind of value or not. Finally, when I have written the value, I am using the notation WI, that's all. You are getting the values in terms of star, and then I am replacing the star values, you know, considering finally the stars are equal to yi minus yi by sigma I, x naught 1, that is 1 upon sigma I, the second x value xi by sigma I, and presented the thing in terms of wi's. So it is your homework to check whether when you are going for GLS, you are getting this value of the estimator or not. And the next task will be to find out variance of beta 2 hat star. The way you do in case of in the ordinary model, you know, in that way only I derived all these values. Because after transformation, it is becoming the classical model. So the steps will be same. It is generalized estimator because we are doing all these things on the basis of the transformed model. Therefore, we are calling it the GLS estimators. However, the procedure of estimation, that is unchanged. The procedure of estimation is unchanged, you know, and the value of the weight, everything is given. So this is homework number 1 and this is homework number 2. Find out beta 2 hat star and find out variance of beta 2 hat star. Okay. Once you get beta 2 hat star, you will find that beta 1 hat star is y star bar minus beta 2 hat star x star bar. It is y bar minus beta hat into x bar format. Okay. And then you can use the notations to write it in a write it with the weights we have considered here. At this particular setting, Wi, which is equal to 1 upon sigma I square, is called the weighted least square, WLS, which is a special case of GLS. Which is a special case of GLS. And it can be shown that beta 2 hat star is unbiased and the variance of beta 2 hat star is less than variance of beta 2 hat. So your third homework will be to show beta 2 hat star is unbiased and variance of beta 2 hat star is less than variance of beta 2 hat. This is the third homework. So the first thing will be calculate beta 2 hat star and beta 1 hat star. Find out variance of beta 2 hat star. Third, show that beta 2 hat star is unbiased and its variance is less than that of the variance of beta 2 hat if I estimate it using the OLS. Everybody got what are the homeworks?
Yes, ma'am.
Now, considering a different weight, I'll show you the variance of weighted least square estimator is less than that of beta 2 hat. This particular setup you will complete. However, I am doing it in a different context. Okay, so again, consider the model in the deviation form. Consider the model in the deviation form. So write down the model as yi is equal to beta xi plus ui. Consider the model in the deviation form. Assumptions. So error is known up to a multiplicative constant. So these are for all i's. Okay, and xi is non-stochastic. This is the setup. Okay, and already we checked expectation of beta hat is equal to beta And please calculate variance of beta hat OLS in this case. Use the formula which we already did. And tell me the formula for variance of beta hat in terms of xi, zi, etc. In this particular context, when variance of ui is equal to sigma square zi square, so in this particular context, tell me what will be the value of variance of beta hat OLS. Look, the formula is already given. You already did it. The formula is summation xi square sigma I square. That was the formula. And here the variance is sigma square zi square. So you have to do only this much. You need to replace sigma I square by sigma square zi square in the earlier formula. Because I need to, keep it. Because I need to compare variance of beta hat OLS with the variance of beta hat GLS. Anyone, please tell me what is the formula?
That would be sigma squared into
Sigma square in
summation xi square into zi whole divided by summation xi square. Sorry, ma'am.
Upali? Is Rudra all right?
Yes, ma'am.
Huh? Yeah.
Ma'am, actually,
Upali,
I can't see the
louder.
presentation and I'm getting logged out 10 times. So, ma'am, my internet connection is very bad. Ma'am, my internet connection is very bad.
So you didn't do the
I
earlier
can't hear
state?
you. Ma'am, I can't hear you.
Else? Anyone else? What is the formula? Yes, Shreya?
Ma'am, it will be summation xi square sigma I square zi square whole divided by summation
I
xi
square
square
from where
whole
you are
square.
getting, Shreya,
Yes,
from
ma'am.
where you are getting I square?
Ma'am, which one? I can't hear you properly.
There is a mistake in your formula. From where you are getting
Yes.
sigma I square?
Oh, okay, ma'am. It will be sigma square into zi square.
Sigma square into?
Zi square means, ma'am, we are putting the variance of ui in this new thing into the formula of variance of beta hat OLS. So the earlier it was summation xi square sigma I square divided by summation xi square whole square. So we are only putting this sigma square into zi square in place of the sigma I square, right?
Yes, yes. Only this much. Yeah, only this much you have to do.
Yes, ma'am. Then it's fine.
Aditya, you want to say something?
No, ma'am, that only I was saying.
Okay, so finally, Aditya, tell me what I'll write.
Ma'am, summation xi square
Summation xi square.
sigma square zi square.
So sigma square, I can keep outside the range of the sun as root of
Yes, ma'am.
Indicate it.
Summation xi square whole square.
So we can write variance of beta hat OLS in this format, sigma square into summation xi square zi square divided by summation xi square whole square of that. Next, let's consider a transformation. Let's consider a transformation I'm considering the square root of the multiplicative factor. The multiplicative factor is zi square. I'm taking square root of that, so it is becoming zi and deflating the entire model by this. Okay. Let Vi. So I need to check the properties of Vi. Now tell me, what is expectation of Vi? Vi is Ui by Zi.
That will be 0.
Expectation of Vi is equal to 0, everyone? It is 1 upon Zi, expectation of Ui. So it is 0. Next, what is variance of Vi?
Sigma square.
You know, will you tell me the steps, calculations?
Yes, ma'am. That will be 1 by zi into expectation of ui squared.
Variance of Vi you need to calculate.
Yes, ma'am. Variance of vi is variance
Ui by
expectation
Zi.
of that will be expectation of vi squared minus expectation squared of vi. That since that is 0, it will be simply expectation of vi squared. So this will be 1 by zi into expectation of ui, variance of ui. Sorry.
1 by Zi.
Zi squared into expectation of variance of ui.
One by Zi square variance of Ui. Okay. So Vi is homoscedastic. And covariance of Vi Vj, since expectation of Ui Uj or covariance Ui Uj is equal to 0, this is equal to 0. So while Ui is heteroscedastic and therefore not a classical error, Vi, that is the transformed Ui, is a classical error. Okay. So, you know, once we get this thing, since the transformed model is a classical model, You can use the ordinary least square technique here. Anyone tell me what will be the value of beta hat GLS or beta star GLS? Say. Estimated value I am marking by star. So, treat yi by zi as yi and xi by zi as xi, and tell me what will be the value of beta star GLS or beta star WLS. What will be the numerator? What is the numerator? This is a classical model. So in a two variable model, what is the value of the estimator? And it is also given here, beta hat OLS is equal to summation xi yi divided by summation xi square. So in terms of the classical model or the transformed model, what will be the value of beta star GLS? You have to do the ordinary least square only and tell me the formula. Nazma, what will be the formula? Left the meeting.
No, ma'am, I'm here.
Okay.
Connection.
So what will be the formula? Arjo, will you try? The formula is given there. So just with respect to the transformed model, you have to tell me the formula.
Ma'am, denominator.
Yes. Denominator, Nazma, yes.
Transform part will be summation of zi square.
Zi squared. Look at your new x, new y. So how I'll proceed? There are so many semesters, and you have to do a lot of econometrics. Everything is in front of you. Just you have to tell me what will be the formula. Shubhangi?
Yes, ma'am.
What will be the formula? What is your new?
Ma'am, can I try?
I want to listen from rest of the students too. What they are doing, I am not understanding at all. Purnima?
Ma'am, it will be expectation of summation xi by zi into ui by zi.
Purnima,
Yeah.
from where the expectation is coming? I'm just asking you what will be the formula for beta hat. No expectation is there. Anyone else? Shreya, in that case, you tell us.
Okay, ma'am. Ma'am, in general, beta hat is summation xi yi by summation xi square. But here we are taking xi by zi. So it will be summation of xi yi divided by zi square whole divided by summation xi divided by zi whole square. Like the summation of the xi by zi whole square.
Okay, so I'm, writing this thing, more easy version, where xi by zi into yi by zi. You have rightly said, summation xi yi divided by summation zi square. So simply I can keep the thing in this way. Okay, so this will be the thing. So this is the simplest thing. I don't know what you are doing, all these things you did at your undergraduate level. So it is summation xi yi divided by zi square, or you can simply write summation xi z by zi into yi by zi divided by summation xi by zi whole square. So this is your beta star GLS. And then you need to check whether this is equal to beta or not. So do the steps. Find out expectation of beta star GLS. Replace yi by zi by beta xi by zi plus ui by zi. Replace this part by this part. Replace yi by zi by beta xi by zi plus ui by zi. And find out expectation of beta star GLS. Today only we did all these steps. We had xi, yi in the denominator, summation xi square only. Now you have to consider everything in terms of the transformed model. Now simply replace yi by zi by these things. So the first value is beta xi by zi. So if you keep beta outside the range of sum, you are getting beta summation xi by zi whole square. That will be cancelled with the denominator. And the second term will come in terms of ui by zi. Rudra got the value? Expectation of beta star GLS?
That is simply beta. That means it's unbiased.
Did all the steps?
Yes, ma'am.
Rest of the students? Are you getting it?
Yes, ma'am. Yes, ma'am.
Once you complete that, remember it is a classical model and you have to write the formula for the classical model. Only x has changed by x by z, y has changed by y by z.
Can you repeat, ma'am?
This is a classical model. Transformed model is a classical model. So in a two variable format, you know what is the value of variance of beta hat OLS. So here variance of beta star GLS will follow that formula only. However, in place of X, you have to write X by Z. And again, in place of Y, you need to write Y by Z. However, the formula will be similar to that of the OLS variance formula. Now, what is the formula for variance of beta hat OLS in a classical model, in a two variable case?
Sigma square divided by summation xi square.
Sigma square divided by summation xi square. It is a classical model. You will have the same formula. In place of summation xi square, you have to write the new xi value, transformed xi value. So Rudra, tell me, what will be the variance of beta star GLS then?
Sigma square divided by summation xi by zi whole square.
Yes. Standard is sigma square divided by summation xi square. That I am replacing by sigma square divided by summation xi by zi whole square. So for the transformed model, now we got the estimator, beta star GLS. We got two properties. Expectation of beta star GLS is equal to beta. So beta star GLS is unbiased. Okay. This indicates beta star GLS is unbiased. Unbiased estimator. And we also got the value of variance of beta star GLS. Is there anyone who is not understanding the variance value? Or who didn't get expectation of beta star GLS is equal to beta? So in the next step, we will compare the two variances. We have variance of beta hat OLS given by this formula. And we have variance of beta star GLS given by this one. We need to compare these two variances. Okay. And we need to check whether variance of beta star GLS is lesser than variance of beta hat OLS. In that case, we will be able to claim the transformed model is giving us the minimum variance. So please write down both beta hat OLS and beta star GLS are linear and unbiased. Both the estimators are linear and unbiased. Next, to compare variance of beta hat OLS with variance of beta star GLS, we consider the ratio. Next line, variance of beta hat OLS divided by this variance of beta hat OLS divided by V of beta star GLS is equal to In the numerator, you write down the formula for variance of beta hat OLS, and in the denominator, you write down the formula for variance of beta star GLS. So variance of beta hat OLS divided by variance of beta star GLS, numerator this value, denominator this value. Then you have to simplify this. I hope all of you are finding that sigma square can be cancelled. So please check whether we can write this as where I kept the pen. Make an adjustment. Not getting the board pen. Yeah, got it. Look whether we can write it as so. Please check this, whether we can write this or not. Everybody got it?
Ma'am, is it variance of beta star GLS by variance of beta hat OLS?
It is, I have to keep it, yeah, variance of GLS divided by variance of OLS, yeah.
Okay, ma'am, I got it.
Okay. Variance of GLS by variance of OLS. This is basically rest of the students, you got it?
Yes, ma'am.
Okay. So now I'm writing it, especially the numerator. Just a minute. As I'll write actually the numerator in the shape of the denominator. Can we write the numerator in this format?
Yes.
Please check, and if anyone have any problem, please let me know. Summation xi zi into xi by zi, denominator summation xi zi square and summation xi by zi square. Is it okay? So this one, where ai, you are understanding, is xi into zi and bi is xi by zi. So please note down that. Any idea now what I'll do? What formula should I use? Because summation ai bi divided by summation ai square, summation bi square, this is related to a particular inequality. Anyone, any idea? Okay, I missed one whole square, I think. In the numerator, I had summation xi square whole square of that. Okay. So I missed one whole square. Nobody told me. I think, only a few people do these things. However, please note that you will have a lot of viva examination. So you need to be active, interact. So whole square of this entire thing, because it was whole square of summation xi square. So, it will be whole square of this entire thing. And therefore, it will be whole square. Whole square of summation ai bi. Okay. So now, by Cauchy-Schwarz inequality, Cauchy-Schwarz inequality, we get I'm clearing this board. Do anyone have any question, any query regarding this? Because I'll erase it. By Cauchy-Schwarz inequality, we present this in this format. Okay. The equality, please write down. The equality sign holds if and only if AI and BI are proportional. Equality sign holds if AI and BI are proportional. In note, please write down, suppose AI is equal to KBI, where K is a constant. AI is equal to KBI, where K is a constant. This implies Zi Xi is equal to K because A was Xi Zi and B was Xi by Zi. Zi square is simply K. Okay. Now what we assumed, what was our assumption regarding variance of UI? What was the formula? What was the formula we used?
Sigma square Zi square.
Just repeat.
Sigma square Zi square.
Sigma square. So if Zi square is a constant, K, in that case, actually we are talking about homoscedasticity. So there will be no difference between the GLS and the OLS estimator. If you estimate the parameters using GLS technique, fine. If you estimate the parameters using OLS technique, fine. You know, ultimately you will get the same value of beta as well as same value of the variances. So equality prevails if AI and BI are proportional. Actually, when AI and BI are proportional, our starting point is homoscedasticity rather than heteroscedasticity. And therefore, we will get the same variances both for GLS as well as for OLS. Okay, so in this way, we can show that the GLS estimator provides the lesser variance compared to the OLS one, and therefore, it is the better estimate. In case of heteroscedasticity, or if I consider GLS in this format, the another name of these GLS is weighted least square. So generally it is said that, you know, we consider the weighted least square technique to get the best linear unbiased estimators in presence of heteroscedasticity. Okay. So this is the second part, how we will derive the estimated value, etc. So, you know, already I presented this model, this transformation, and I gave you several homework So find out these estimated values, etc., and following the same rule as I discussed now, you check whether variance of beta hat star is less than variance of beta hat. Actually, this is the GLS estimator, this is the OLS estimator. So consequences done, remedy done. Okay, or what will be the technique of estimation, etc. Next, we need to learn about the detection. Given the data set, how we will detect whether there is heteroscedasticity or not. Okay, so detection. First, we start with the graphical thing. It is note that graphical presentation will be able to tell us the matter in the best way, because graph has always a limitation, it is two-dimensional. Okay, so only one explanatory variable you can choose. If I plot basically the EI square, the square of the residual across x values. So in that case, you can consider one explanatory variable at a time. However, to start with, given the data, etc., we can use the graphical method. At your undergraduate course also, you learned about several detection methods like White's test, Bruch-Pagan test, etc. You found that in case of heteroscedasticity, we try to relate the residual component with xi. That is whether there is any relation between xi and the residual component. If there is any relation between the residual component and xi, in that case, there is a chance that there is heteroscedasticity. So as rule of thumb, if we use the graphical method, we may consider one explanatory variable at a time, and we can plot EI square or U hat square. U hat is equivalent to E, the residual. The square of the residual you can plot against X. So here I have presented different shapes, So if there is this kind of pattern between the residual square and xi, there is a possibility of heteroscedasticity. If there is no pattern in this kind of presentation, in that case, probably the situation is homoscedastic. Okay, I mentioned graph is not a formal method or objective method. However, graph always present everything very vivid. Okay, so we cannot avoid graph. So you can do this kind of graphs and you can check whether there is any relation between residual square and xi. If you get the relation, you can argue that there is possibility, there presence of heteroscedasticity. Now, always it is best to go for formal tests. So there are several tests to detect heteroscedasticity. We can start with White's general heteroscedasticity test. Now, for all heteroscedasticity tests, in the null hypothesis, we will consider homoscedasticity or no heteroscedasticity kind of context. No heteroscedasticity. Okay, so we are considering a multiple regression structure. Yi is equal to beta 1 plus beta 2 x2i plus beta 3 x3i plus ui. In the first step, we will do the OLS. Given this model, we will do the OLS and we will find out the residual. We will derive yi minus yi hat and that will give us the residual. So in the practical session, now you learned how to estimate a regression model. So you can estimate the regression model and you know how to find out the residual. run the following model with the covariates and their cross products. So what I'm doing, now I'm considering the square of the residual, and that I am regressing on x2i, x3i, their squares and their cross products. Okay, so in the White's test, first you need to find out the residual, and then is the regress residual on x2i, x3i, their squares and their cross products, and derive R square. Next, step 3, we can consider NR square. I hope you can remember several large sample tests we talked about, the world test, LR test, LM test, etc. I gave you the note on that. So we are running, you know, that kind of test. Anyone will be able to tell me what particular test I am doing here, LR or LM or world? Already the note is with you. Okay, so check what test actually we did. The likelihood ratio test or Lagrange multiplier
This
test?
is the LM test.
This is the LM test. Yes, very good. So Lagrange multiplier test we need to do. Lagrange, in case of Lagrange multiplier, this is the test statistic and it follows the chi-square distribution with k-1 degrees of freedom. If you find that this chi-square is greater than that of the critical one, you need to reject H naught. So in the theory paper, given a very small data set, I hope everybody will be able to calculate this kind of, everybody will be able to, you know, estimate the parameters of this kind of regression. Once you can estimate the parameters, apply LR test. Actually, you need to find out R square. Sorry, LM test statistic is given by number of observation into R square, and that follows chi-square. Once you calculate this value in R square, you will be able to compare it with the critical chi-square, that is chi-square at 5% level, 1% level, etc. So if the estimated value is greater than the critical value, you need to reject H naught. These rules you know, how to reject or when to accept, this you know. So look at these steps very carefully, very small thing, you know. However, think about a situation when you have data and when really you need to run this test and really you need to claim whether there is heteroscedasticity or not. Any question? Is White's test understandable to all of you? Now, if I increase one more explanatory variable, say x4i, in that case, you need to regress the square of the residual on x2i, x3i, x4i, then x2i, x3i square, x4i square, and then all the cross products. So if the number of variable increases, here also the number of explanatory variables will increase. Okay. So today I'll stop here. There are few more tests, you know. Goldfeld quant test. You are familiar with this. Bruchfagan-Godfrey test. There are several other as well. However, these three tests are most important. So I'll discuss Goldfeld quant test, which you did already in your undergraduate course. Bruchpagan Godfrey test. These two tests I'll discuss in the class. Okay. In the meantime, please check the consequences of heteroscedasticity, how we are using the GLS technique to find out the best estimators, detection, how we can do it using the graph, what is White's test. There is an example too. Here there is an example, okay, of this is an application of White's test. Okay, so this is done up to derivation of R square. So there are two questions. Can you compute the White's test statistic here? What will be your conclusion about heteroscedasticity? So you complete up to this. For these R square, find out what is the value of NR square. Consider the test at 5% level and check whether the error is heteroscedastic or homoscedastic here. So complete up to this, and in the next class, I'll discuss these two, and after that, I'll shift to autocorrelation. Okay, so by next Thursday, we will complete the discussion on error term. Twinkle, absent. Titir, there are few people waiting. Anyone is waiting or?